This is Jack Jackson. In this video we're going to talk about how we can use precalculus, calculus, and technology together to analyze the graphs and characteristics of some functions, and in particular we're going to look at families of functions. In some of our previous videos we looked at a specific function and analyzed it, but in this case we're going to look at a whole family of functions at once. So we're going to use here the letter x to represent the input as standard, and f, or f of x, to represent the output. That's also standard for functions. But then there are going to be other letters in the formula, like maybe a or b or c, and those are constants. But they're arbitrary constants that can vary from one function to the other, and this puts together an entire family of functions for the different values of a, b, and c, giving us different members of that family of functions. Those numbers a, b, and c, the constants that can be changed, are called parameters for that family. So what we want to do is analyze a family of functions. In this video we're going to look at this one right here. F of x equals a, parentheses, 1 minus e to the negative bx, close parentheses, plus c, where a, b, and c are real numbers. But a, b, and c are constants again. Let me emphasize that. So once again, x is the input variable here, f of x is the output variable, x and y, or x and f, but the a, b, and c are constants. So what we want to do is do the things that we normally do when analyzing functions. We want to actually draw some graphs of these, and we'll use some technology for that. I'm going to use Graphmatica for the graphs, but you could use other programs for that, or even your graphing calculator. And we're going to talk about all the kind of interesting things like the domain, the range, the x and y intercepts, the global and local extrema, any inflection points it might have. We'll talk about the direction and concavity of the graph, if it has any discontinuities, any endpoints, asymptotes, and then end behavior. And so, in short, any kind of interesting thing that we might find about the function, we're going to try to do that. But notice that when we do this, for example, we're going to find the derivative of the function and find the second derivative. So both first and second derivatives. But the first and second derivatives, as well as the original function, have these a, b, and c values in them. And so, in general, when we find things like, for example, critical values or extrema or inflection points, those will be ordered pairs for the extrema and inflection points, but those ordered pairs won't be specific numbers. They'll be functions of a, b, and c. Okay, so let's take a look at this. Well, let's take a look at this. We can take any number x and multiply by negative b. We can always raise e to any real number power. We can subtract that from 1. We can multiply by a. We can add c. There's absolutely nothing in this function that would cause an illegal kind of an operation. So in fact, x could be any real number, really regardless of what a, b, and c are. So the domain is the set of all real numbers. So it's really just a transformed exponential function. So one of the simplest members we could look at would be to, let's say, b be 1, a is 1, and c is 0. So that would be f of x equals 1 minus e to the minus x. And that's what we have graphed right here in blue. So there's a typical example, or a basic, let's call that our basis example, or a basic example. So, in fact, this function we could further think of as just an exponential decay function that's been flipped over the x-axis and then shifted up 1. Now, if we take that specific function above, and what happens if we change the value of a? So for now, let's leave the c 0 and the b 1 and just change the a. Well, notice changing a is the same as replacing y, or f, by, say, y over a, would produce the a value here by multiplying both sides by a. So we know in general that if you replace y by y divided by a, that gives us what we call a vertical strain by a factor of a. So everything is going to leave the x values alone and multiply the y values by a in the table. And what that does is gives us what we call a strain or a stretch or compression in the vertical direction. That is if a is positive and not 1. If a is negative, then in addition to any kind of a stretch we might have, the graph is also reflected over the x-axis, because that's the same as changing the sign on y. One thing we may notice right away is if a is 0, then the graph degenerates to just the x-axis, because this whole term becomes 0, and you get y equals c, which at the moment we're taking to be 0. So there is a graph here where it's just the x-axis. That's where a is 0, and then these other graphs you see here. So basically the blue one here is the one we looked at before. Okay, that's the one where a is 1. Okay, and all of these, where it's increasing concave down with an asymptote on the right, those are the ones with the positive a's, and the negative a's we have basically reflections down here, so that we are decreasing concave up with an asymptote that's negative down here. And specifically, I'm looking at these values for a, -10 to 10 going up by 1s, or the ones that I have graphed. And the way this works here, these are actually -10 is the one here, so it's -10, -9, -8, -7, -6, -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 for the value of a. And all of these have b as 1 and c as 0. So you kind of get an idea of what a does to the graph. In a similar manner, if you look at the formula up here, changing b from, say, 1 to some other number b is replacing x by b times x. Okay? Which, if you multiply x by b, what you really do in the table is you leave the y values alone, and you multiply, actually divide the x coordinate by b. Okay? Now what this does, it gives you a horizontal strain. So it stretches it or compresses it horizontally by multiplying the x coordinates by 1 over b, actually, or by dividing them by b. So here we go again. Again, the one in blue is the one we started with, and we can think of transforming it by stretching. Once again, if you change the sign on b to a negative number, you're going to get a reflection. This time, it's a reflection about the y-axis. So these are set up here. So the ones with a negative b have a horizontal asymptote on the left, and then go towards negative infinity on the right, whereas the ones with a positive b go to negative infinity over here on the left and have a horizontal asymptote on the right. So in fact, let's see, I think these actually are, here are the different values of b that I did, and let's see, if we do those in order, we actually start here with this one on the right here, which is, so this one's actually -2 for b, this is -1.8, this one right here is negative 1.6, the -1.4, -1.2, -1, -0.8, -0.6, -0.4, -0.2, and 0, of course, is just the x-axis for the a. And then with the positive ones over here, 0.2, still working my way from right to left here, down here, 0.2, 0.4, 0.6, 0.8, and then 1, 1.2, 1.4, 1.6, and 1.8, and then 2. So 2, 1.8, 1.6, 1.4. Okay. Alright, so that gives you kind of an idea of what those look like and what changing b does to the graph. Now, look back at the formula again. If you'll see that changing c is really the same as replacing y by y minus c, and that's just going to give you a vertical shift, a translation. So here again we've kept a and b both 1. We've chosen these values for c, and we see shifts of that, so vertically. Okay, so these are just vertical translations. This one has c as -8, -7, -6, -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, 6, 7, 8. The horizontal asymptote is always just c plus 1 in this case. And the y-intercept in this particular case is the c value, 0c. Now, of course, you can put these together. We don't have to always leave something fixed, so we can change several things. For example, what if we let a be -2 and b equals 3 and c equals 4? Well, this is the formula that we get right here, and this is the graph we get. So we could think of this as taking that original one that we had above, the one that's in blue right here, or this first one that we graphed, which is just y equals 1, parentheses 1 minus e to the, you know what, let me just go ahead and type that formula in here. So what we're doing is we're letting this be 0, this be 1, and this be 1. Or if we just simplify that, we don't have to, we could just write it like that. And that's the function that I have graphed right down here. Right there. So anyway, take that one and turn it into this one down here, and we'll see what happens. You can think of this in this order by first changing the a to -2, which is going to reflect it over the y-axis, over the x-axis. Let's see, wait a minute. Yeah, x-axis. See, change the sign on y, reflects over the x-axis. So reflect it over the x-axis first, then stretch vertically by a factor of 2, so it's twice as tall or twice as far from the x-axis. Then it shifted up 4 units by the 4. And last I took care of the change on the x, which is replace x by 3x, which will compress it horizontally by a factor of 1/3. It's 1/3 of the way. It's only every point is only a third as far from the y-axis. Okay. Now, if you want to think of these things in order, it's important because if they're going to phrase it the way I did here, that we take care of, because of the order of operations, we take care of what's happening with this -2 here first, and then take care of what's happening with the 4. Now, next, notice that there is a degenerate subclass of this family. So if you go back up here, and you either let a be 0 or b be 0, this thing reduces to just y equals c. Now, to see that, if a equals 0, it doesn't matter what this is. All this stuff times 0 is 0, and 0 plus c is c. If b is 0, the opposite of 0 times x is just 0. Either 0 is 1, 1 minus 1 is 0, 0 times a is 0, and 0 plus c is c. And so either way, if you let a or b be equal to 0, then the whole thing degenerates to just y equals whatever c is, which is a horizontal line. So this does include this sort of subclass of this, which is where we have horizontal line. And but in a way, this is sort of a degenerate subclass because it would be much easier to write the formula as just y equals c for those functions. So below we will assume A and B are both non-zero most of the time. Okay. Now so far we've just been graphing some things and kind of seeing what we've seen and kind of describing that, and we've used a little algebra to explain what's going on in terms of transformations. Now let's use some calculus to verify and generalize some of the characteristics that we've been seeing in some of these graphs. So first, at least the non-degenerate examples lead us to believe, so far, it looks like we're going to get a horizontal asymptote on one side, but not the other side. Either on the far right and none on the left, or in some cases the far left and none on the right. Okay, so to see that, let's look at what's happening in the end behavior. We're going to take limits. So let's see if we can look at these limits here. Take the limit as x goes to infinity. Now, if b is positive, let's take that case first, then we have the opposite of b would be negative, and we put in a larger and larger value for x, which is positive. This power then is a negative power getting larger and larger and larger in absolute value. And so e to the negative something, it's like e to the negative infinity. That's approaching 0. So the limit of this little piece right here would be 0. 1 minus 0 is 0, 1 minus 0 is 1. There we go. And 1 times a is a plus c is a plus c. So if b is positive, this limit is a plus c. And so that would tell you that on the far right, you're going to have an asymptote of y equals a plus c when b is positive. Now what if b is negative? Well, if b is negative, then you've got two negatives here, which make a positive, times x. X is going to infinity. This whole thing is going to infinity. Well, the minus in front makes it go to minus infinity. And then if a is negative, then that's going to flip it back over to positive infinity. So if b is less than 0 and a is less than 0, it approaches infinity on the right side. So it's going up forever. I don't think I've graphed one like that case yet. On the other hand, if b is less than 0 and a is positive, so b is negative and a is positive, again, b is negative, so this is going to e to the infinity. So this whole thing is going to infinity. The minus makes it go to minus infinity. Add 1, still going to minus infinity. But we're multiplying by positive a, then that whole thing's going to minus infinity. Add c, we're still going to minus infinity. So, in fact, the whole thing goes to minus infinity on the right side. And we did look at an example like that one. These examples right here go to minus infinity on the right side. And similarly, we get the same sort of thing with x goes to minus infinity. It just changes the sort of the signs on it. When b is negative, then that gives us negative, negative, negative. 3 negatives makes a negative power here. So basically, it's going to e to the minus infinity. So it has that form anyway, which is approaching 0. So as this limit of this little piece right here goes to 0, 1 minus 0 is 1 times a is a plus c is a plus c. So on the left side, you have an asymptote of a plus c when b is negative. And I think we looked at somewhere b is negative here. And that's all of these that go to minus infinity on the right go to a plus c as your limit on the left. So it has an asymptote on the left side. And similarly, you can work out these here. Let's kind of go through that again. If b is positive, that's positive. The negative here is negative. We're going to negative infinity, so there's another negative, so that makes a positive exponent going towards infinity, which means the e to that's going to infinity. The minus makes it go to negative infinity. Add 1, still going to negative infinity. Times a, if a is positive, then the whole thing's going to negative infinity plus c is still going to negative infinity. On the other hand, if a is negative, the negative infinity here times the negative makes the whole thing go to positive infinity. So, what's the conclusion from all this? Well, the conclusion is that y equals a plus c is an asymptote on one side or the other, but not both. Okay? It's on the right when b is positive, and on the left when b is negative. Okay? So, but either way, y equals a plus c is a horizontal asymptote. It's either on one side or the other. And on the other side, it either goes towards infinity or negative infinity. For example, in this graph here, let's see, we have a positive b, because remember the negative was built in. Positive b, negative a. That's going to give us the asymptote of a plus b on the right. A is negative 2, b is 3. That adds up to 1. Let's see, wait a minute. No, a plus c, excuse me. That's what it's supposed to be. Negative 2 plus 4, that's 2. And there's your asymptote is 2. It's a plus c, right? Yeah, a plus c. And that happens when b is positive, and b is positive here. It's 3. And we're going off to infinity over here. Now this is a function, and 0's in the domain, so it will have a y-intercept and exactly one of those. And so notice all you have to do is evaluate f of 0, plug in 0 for x here. Well, negative b times 0 is 0. Either 0 is 1, 1 minus 1 is 0, 0 times a is 0, and 0 plus c is ultimately c. So 0c is your y-intercept in this case, in every case. So one of the things that we see, regardless of the value of a and b, we know that y-intercept is just the same as c. So that's kind of a nice little thing to see. And the y-intercept is really not affected by the values of a or b. Now, there's an x-intercept at, let's see here, at this value right here, the opposite of log of 1 plus c over a over b, of course, comma 0, because it's an x-intercept. And this will happen when the 1 plus c over a is positive. Notice that happens exactly when, let's see, subtract 1 and multiply both sides by a. We get c is greater than minus a. And you don't have an x-intercept because that expression is undefined whenever c is less than or equal to negative a, because the domain of the logarithm is only positive. So the 1 plus c over a has to be positive. How did I get that expression? Well, I just set 0 equal to the f or y or the output equal to 0 and set that equal there and solve. So I subtracted c from both sides, divide both sides by a. Subtract 1 from both sides to get here. Take the logarithm of both sides. When I divided both sides by 1 here, the negatives all cancel out. Take the logarithm of both sides, or rewrite as a logarithm when we get the power. The logarithm, the power, minus bx, equals the logarithm of this side. And then divide by negative b, and we've solved for x. Okay, so again, this is undefined when 1 plus c over a is negative or 0, which corresponds to be c less than or equal to negative to the opposite of a. But if c is greater than the opposite of a, this is defined and it gives you a point. So sometimes you don't get a y-intercept, an x-intercept like this purple one here. Or if you look at some of these ones down here don't get up to the x-axis, but all these others do at some point. We'll see a little bit later on that this is an increasing function, so that makes it's either all increasing or all decreasing unless it's a horizontal line, and that's going to give us the fact that the function's actually 1-to-1 when it's not just a horizontal line. Through that. Now let's find a derivative. Okay, so here's the original function here, and we want to put the derivative of that. So that's the first derivative. Okay, first of all, I'll use the sum rule. The derivative of c is 0 plus the derivative of this part. Then I use the product the constant multiple rule. Remember, A and C are constants. So the A comes out front, and I take the derivative of what's left. Now I use the sum rule again. The derivative of 1 is 0, and then I'm just taking the derivative of this exponential here. This is e to the u, so you get e to the u, which is e to the minus bx, times the derivative of that, which is minus bx. We also have this negative 1, which I put out front, which goes out there as a coefficient. That's the constant multiple rule for that part. So, let's see, it looks like we got two negatives. That'll multiply together to be a positive. So we get a times b times b times, a times b times e to the power of negative bx. Now that actually is fairly simple looking little formula. Now, of course, remember we had our degenerate cases when either a or b equals 0, and that makes the derivative 0 regardless of what x is. And then, of course, that tells you that you have a horizontal line, and that's what we already saw before. The derivative is always 0. It's a horizontal line. Now, the e to whatever power is always positive. So if a and b have the same sign, either both positive or both negative, when you multiply you'll get a positive, and the whole derivative is positive. The derivative is positive when the original function is increasing. On the other hand, if a and b have opposite signs, either a is negative, b is positive, or a is positive and b is negative, then when you multiply all that out, you're going to get a negative value for f prime of x, and that is enough to tell us that the original function is decreasing. So, bottom line is, when a and b have the same sign, the first derivative is positive, the original function is increasing. When a and b have opposite signs, the first derivative is negative, and thus the original function is decreasing. Now similarly, we can compute the second derivative. It's not too hard here. We have ab e to the minus bx. Now when you're computing these derivatives on these families of functions, you've got to keep track of which letters are constants and which are variables. Of course, e is a specific constant, standard constant that we use a lot. And a and b, however, are constant parameters. We don't know what they are specifically for a specific example, but we do know it is some constant. Well, that means we can use the constant multiple rule and factor out the a and the b and take the derivative of this. The derivative of e to the u is e to the u times the derivative of the u. Derivative of bx is minus b. So we got minus b times b is b squared, minus out front, then times our a, and times that. So the second derivative is the opposite of ab squared times e to the minus bx. Now this time notice the e to the power and the b squared, because it's an even power, are both always positive. And then so as far as the sign goes, it's just the sign of a and then flipped over backwards because of that negative out front. So, again, in the degenerate case where either a or b is 0, the second derivative is 0 everywhere. Second derivative of 0 everywhere means that your original function must be linear, which is, of course, what we saw earlier. In fact, it's horizontal line. Now, but if the second derivative always ends up having the opposite sign of a. So if a is positive, the function is always, let's see, these are backwards, negative. If a is negative, the function is always then, let me say that again, the second derivative is positive. The derivative is increasing, and the original function is always concave up. And if a is positive, the second derivative is negative. The first derivative is decreasing. And the original function is always concave down. Either way, there are no inflection points. The concavity is all the same. So it turns out that there are five basic classes of examples based on the sign of A and B. Basically 5 combinations we can look at. So here they are. The first case is if the degenerate case is if either A is 0 or B is 0, regardless of what everything else is. You get a function that's just y equals c, whatever c is, which is just a horizontal line. So for example, if A or B are 0, either one or both, and c is 5, we get y equals 5, which is a horizontal line right here. Now if A and B are both 0, the original function should be increasing, concave down, and has an asymptote of y equals a plus c on the right. Goes down towards negative infinity on the left. Here I have graphed where A and B are 2 and 3, respectively. C is 4, and sure enough, there's your graph with those characteristics. Okay, what else? What other cases do we have? Well, we have A is positive, B is negative. So in this case, the original function is decreasing, concave down, and has an asymptote of y equals a plus c, this time on the left. An example I used here was A is 5, B is negative 3, C is 2, and you get the graph here. There's your asymptote on the left. This one's decreasing, concave down. Alright, what about if A is negative and B is positive? Then the original function is decreasing, concave up, and y equals a plus c is the horizontal asymptote, but this time on the right. So here we have it. Here's the original, or here's the new function here. A is negative 2, a negative number. B is a positive 4, and C is 6. And there is our graph. Okay, what if A and B are both negative? Then the function is increasing, concave up, and it has y equals a plus c as the asymptote. This time, however, on the left. You can see that. So basically your graph has to be one of those basic shapes there. Okay, I think that kind of goes through that. So I've got a few more. I may add some videos on these before too long. But here are some other examples to look at. This is very similar to the one we just did, but it sticks an x in there as well. See what that does to the graphs and tables. So I'm looking at the formula or family of formulas. F of x equals a times x times e to the minus bx plus c. And again, let the all reals be what you're working with here. Then I have a couple others. F of x equals e to the ax times sine of bx plus c. Again, a, b, and c are real numbers. And then another one, f of x equals x to the p times sine of ln x. Let me say that again. Where was I? Here we have e to the ax sine of bx plus c. Okay, or here we have x to the a times sine of bx plus c. So we have a trig function times either a power function or an exponential function, and we add a c on the end. Look and see what that does to it. Okay, so you can try to look at these yourself, and then come back maybe for some other videos in the future and see what happens with those.